Hi everyone. So again, Artem Agishin from UC Santa Cruz. So this is a paper that we recently resubmitted about this is a generic interior structure model for steam worlds. So what you see on this animation is an actual result from that modeling. So we consider pure steam atmospheres and pure envelopes and how they contract in time. So it's a 1D model that solves the equation of energy balance with up-to-date equation of state for water in the deep interior, and also revised opacity tables in the atmosphere to control the energy flux. And so that creates new mass radius relations. Also, we reassess the water mass fraction in sub-Neptunes. And one interesting result is that we know that steam atmospheres and hydrogen helium envelopes, they are degenerate. We cannot tell which is which, but this model shows that they have different contraction rates over time. So this is the figure on the right. And we argue that if we can populate the exoplanet space in the radius age and not just mass and radius space, then we can possibly distinguish these two at the population level. So yeah, happy to tell you more around my poster.
We'll hold the applause until the end for everybody's. Okay.
Hi, I'm Marcelo Barraza from MIT. I will have a poster about the outer disk, but it's related to how the material from the outer disk moves to the inner disk, which is induced by gas turbulence. And the direct measurements of turbulence from ALMA observations have used a very simplistic prescription that is using a micro turbulence value, which includes a line broadening in the CO line. What we did is to predict what happens if you include the size scales of the turbulence eddies, post-processing an MRI simulation. And here in the bottom right panel, you see that they give very different results because the large scales move material around and blue shift and red shift a lot of material. So I think we need to revisit that prescription and try to improve it to get better constraints of turbulence. So please come to talk to me if you are interested.
Okay, Eric, where are you? Oh, wait, I'm here. Okay, so I have a poster. Come see it and talk to me. This is sort of a new idea for how we might explain the diversity of disk evolution, as well as the trends that we see of disks evolving dependent on stellar mass and other parameters. And the idea is that the governor of this evolution is actually the innermost disk and what's happening there, and the presence or absence of a wind, depending on the rotation period of the star, the strength of the magnetic field, and the accretion rate. And this actually has some fun other things that it might explain as well. So please come and see my poster and talk to me about it.
Hello everyone, I am Yuki Kambara, a PhD student from the University of Tokyo. I'm working on the planetesimal accretion in a planetesimal ring. So classically, planetesimal are assumed to be a smooth disk, and we know the isolation mass, assuming the smooth disk of planetesimals. But recent simulations have shown that planetesimal can be formed in a narrow ring, and we are trying to figure out how the planets distributed in from when they start forming from a planetesimal ring. And we performed a series of n-body simulations. The right-hand side, it shows the result, major axis versus mass of protoplanets, and we changed several initial parameters, like initial ring width, total mass of planetesimals, and ring location. And we find that, interestingly, the protoplanets distribution does only weakly depend on the initial ring width, and also the protoplanet mass only weakly depends on the initial ring location. In detail, please stop by my poster. Thank you.
I know this is great. This is a great poster.
Hi, I'm Eiichiro Kokubo. in this project, we are interested in the orbital architecture of planetary systems formed by giant impacts. So giant impacts are thought to be the final assemblage stage of the terrestrial planets. So we know the giant impact stage is very stochastic because it's a few body problem from the several embryos to planets. But we try to find some basic rule for this stage. So we performed n-body simulations to investigate what determines what probability of planetary systems. Then we find the very fundamental, simple scaling law. So if we scale at the orbital separation of two adjacent planets and also the eccentricity with this length scale. So length scale consists of the escape velocity, two-body surface escape velocity over the Kepler velocity times the semi-major axis. So then the orbital separation and eccentricity are given by these numbers, which are independent of the mass of planets and also the location of planetary systems. It seems very general. So let's discuss in front of my paper, our poster. Thank you.
Hello, I'm Man Hoi Lee from the University of Hong Kong. So this poster is based on a paper that I published with my student, Kaho Wong. And what we argue is that we have many observed resonant chains with relatively low mass planets, which should be migrating according to type 1 migration. So if they form far out in the disk and they're still all migrating, there are certain conditions for disk parameters for the resonant chains to be maintained while they're all migrating. And it turns out that in many of the cases, those require rather unrealistic disk parameters, including, in most cases, only for logarithmic gradients of the surface density and temperature, which are actually increasing outward. And so we then argue that the more likely scenario is that the innermost planet probably stopped near the inner edge of the disk, and then with all the other planets still migrating inward, then they can be locked into a resonance chain. And so that's the evidence for that comes from for the known system, the location of the innermost planet versus the stellar mass, which you expect a certain scaling if the inner edge is related to something like the magnetospheric truncation radius. So the bonus from the paper is that I've updated the plot on the right with some of the systems that VEDAI has for the young and intermediate age systems. Thank you.
Jack Lissauer, NASA Ames. My poster is on a paper that presents a new catalog of Kepler planet candidates. And this catalog, the focus is on understanding the planets, not as much on the demographics of the population occurrence rates. But we want to get which candidates are very likely to be real planets and which are not, the detailed properties of those planets as accurately as we can, and especially a focus on the orbital periods, including a theoretical analysis for many dynamically solved systems through TTVs of how the measured orbital periods during the Kepler epoch for these systems would change if you had a 4-year observation at different times. So there's a lot of things in this paper. It is going to be on NextSci at some point in the not too distant future, at least most of the properties. We have a huge number of properties, a lot of theory, but we try and present it with a lot of words too. So the poster is going to be on the Blackboard side, the nearest to here. Go take a look, and if it's relevant to your research, dive into the paper.
Hi everyone, my name is Byron Portilla. I'm a postdoc at Penn State. Title of my poster is Protoplanetary Disks in Extreme Irradiation Environments. This is a JWST view of the NGC 6357 star forming region. This is part of the Extreme Ultraviolet Environments program. In this program, we aim to investigate the effect of strong external irradiation on protoplanetary disks. In this program, we report JWST MIRI observations of 12 protoplanetary disks in the NGC 6357 star-forming region. NGC 6357 is a high-mass star-forming region that is located at 1.7 kiloparsecs. And one of the interesting things that makes this region special is that it has a lot of more than 20 OB-type stars that impact the thermochemical structure of planet-forming disks. So we perform numerical modeling to study a subset of these disks, and in particular, the one that my poster is about is the XUE1 disk, which is that disk that is indicated by the white circle in the image, which you can see is basically surrounded by at least 5 O-type stars within 0.5 parsecs. We find that the mid-infrared spectrum of that disk can be explained by distruncation and gas depletion beyond 10 AU, which is consistent with an FUV-driven photoevaporation scenario. If you're interested in learning more, reach out.
Yes, so I'm very happy to represent the H-Pro collaboration. So we have a large program with ALMA trying to measure the gas mass and gas disk size throughout the lifetime of protoplanetary disks. And this is very important because depending on the mass that we have in gas is the type of planets that we can form, also how they migrate, and also how the dust evolve in disks. But before this program, we really didn't know about how is the mass in disk and also how it evolves with time. So for that, we have ALMA large program targeting 30 protoplanetary disks in 3 different star-forming regions, from 0.5 million years old to around 5 million years old. And we have 10 disks in each region, in Ophiuchus, Lupus, and Upper Sco. We have a narrow stellar mass range because we didn't want to have very large dependencies with the stellar mass, so it's something between 0.5 to 1 solar mass. And this is the overview of the main results that we have in H-Pro. So we are 1 paper away from all being accepted, so this is going to be soon in archive. But you see how is the dust disk mass evolving versus the gas disk mass. And we were very surprised about the gas disk mass behavior because, as you see, it doesn't seem to evolve so much from Lupus, that is around 1 million years old, to Upper Sco, that is between 3 to 5 million years old. And because of that, we have this binomial behavior of the gas to dust mass ratio. But we also have results of the dust disk size and the evolution, the gas disk size, and also the ratio of the sizes between the gas and dust in disks, CO abundances, and the spectral index. So yes, please come along to my poster and ask me more questions if you have. Thank you.
Hey everyone, I'm Yan Song from University of Toronto. So the first stage of the planet formation is still not fully understood, mainly because we don't know the dust size in the protoplanetary disk. And have it grown to the pebbles yet? So to tackle those questions, I turn to the Upper Scopia. It is the only surveyed star-forming region with age greater than 5 million years old. So it represents a unique stage in disk evolution. In the poster, I will present the 3 millimeter survey of this region. And I will focus mainly on the size-luminosity relation shown in the right, and how it is different from the younger region. More importantly, I will show what physics are required to explain the observations.
Hello, my name is Aníbal Sierra, a postdoc at University College London, and in my poster you can find the results from a recent paper where we analyzed the dust continuum observation of L-Calfa 15 at band 3. We compared the dust continuum map with previous observation at several wavelengths, and here you can see the main results. From the spectral energy distribution, we found that the spectral indices in the inner disk are very different compared with the spectral indices from the full disk. In particular, the spectral index in the inner disk is consistent with free emission, probably coming from an ionized jet or a disk wind. And from the morphology of the disk, we also find that the rings are narrower at longer wavelengths. So this is consistent with dust trap signatures from different models. So if you have many questions or more questions, please come to my poster. I'm happy to clarify them. Thank you.
Hello, I'm Bennett Skinner. I'm a master's student at McMaster University. When we were talking about the radius valley earlier, you can see that there's basically a difference between you either have the sub-Neptune planets having some hydrogen-helium envelope, or you having them have quite a bit of water. Differentiating between these two is pretty difficult observationally because of degeneracies, but if you actually have some model of planet formation, you know what the planets are made out of because you made the planets. So all you need to do is take the masses and compositions from this planet formation model that you've built and then run it through some type of internal structure model to get the radii. And then you can compare those radii to observations and see if you're actually reproducing the observational radius valley. I have updated I've updated the internal structure model previously used for a population synthesis model at McMaster University and applied it to the radius valley. And as you can see here, whenever you exclude all of the hydrogen-helium enveloped planets, you can still see that the sub-Neptune peak has a secondary contribution from water-rich planets. And I know that they don't match up exactly. If you want to dig more into that, you can ask me at my poster. Through building this new interior structure model, I also now have something that can be used to create new mass radius relationships for the types of curves that you see a lot in planet discovery papers.
Hello, I'm Emerson Chow. I'm an undergraduate student at UC Santa Cruz, and I'm studying water escape from sub-Neptune steam worlds. Volatile-rich sub-Neptunes have the potential to be water worlds with up to about 60% of their water mass. And for planets that are very close in to their host stars, this water reservoir is evaporated into a steam atmosphere. And I have built a model that combines a steam world interior model and atmospheric escape model to study these planets' evolution over time and tracking their mass, radius, and water mass fraction over time. And this model can be applied to real planets like Kepler 18b up here, but more importantly, we can use it for generated planet populations within typical sub-Neptune parameters, specifically steam world parameters. And we notice that after evolving them over time, these planets either larger mass sub-Neptunes hold on to their steam atmospheres, but lower mass planets tend to lose them. And this actually recreates the bimodal distribution that we notice in observed sub-Neptunes, which means maybe steam worlds are more common in the universe than we think, or maybe that's part of the reason of why we have this radius gap. So if you have any questions, feel free to chat. I have a poster over there, so yeah.
Hello everyone, I'm Mu Tian Wang from Nanjing University. I'm a PhD student. So you may have known from this morning's talk that for the youngest planet, they are still evolving dynamically and losing their atmosphere in the first 100 million years. This is not only true for single planet system, but also true for multi-planet system. So there has been some observation constraints that this very young multi-planet system show a very high resonant fraction. That is a very natural outcome of the disk migration. So it is reasonable to see a very high resonant fraction right after the disk disposal. But this fraction seems to decrease on a 1 giga-year timescale. So there might be a dynamical sculpting process that is responsible for the lower resonant fraction we see in the mature Kepler planet system. And so in this work, we are looking into a particular system that is right at the age bin where this dynamical sculpting is about to occur. And what we found is that this system, despite being probably a resonant planet system, is in a circulating near-resonance configuration, which is statistically unstable. And also we found some evidence that this system at the age of 300 million years old might have concluding photoevaporation. So if you want to learn more about the system, please come to my poster. Thank you.
Hi, I'm Morgan Williams. I'm a PhD student at Imperial College London. I'm working with Subbu Mohanty. My poster's divided in two parts, one leading into the other. To talk you through the first part, we've worked on an ionization chemical network for the inner disk. And we've built upon previous works that have included some of the components and some of the physics. So what we've got is we've got electrons, alkalis, and crucially, an arbitrary distribution of grain sizes. Some of our key physical components are the thermal and non-thermal ionization processes, but we've also got some key grain processes, which are ion emission and thermionic emission. And these are emission processes that occur from the grain surfaces, actually enhancing ionization fractions in the inner regions. And furthermore, we've got a size-dependent grain charging. So if we look at this plot here, we can see that with different distributions of grain sizes with other properties held fixed, we can find that the abundances that we derive of all these components vary by several orders of magnitude. Crucially, the electron abundance is the most significant for determining resistivities for MHD calculations, which we'll perform later on. And so if we look at the charges that we get on the grains, we find that around 1,000 Kelvin, which is probably roughly where we're at for the inner disk, these ionization processes that occur on the surface of grains actually gives us very large negative charges on these grains. And this has two important effects. So the first is that it affects the range of the impact parameters between two grains that can result in collisions. So this affects the rate of collisions between grains. It also affects the collision velocities. Now this has also affects the rate of collisions between the grains, but it further affects the collision outcomes. So these grains are decelerating as they approach one another because of their like negative charges. And so now if we look in this bottom right quadrant and we look at the orange and the green lines, if we look at the top solid orange and green lines, these are for the charged dust, and they're the collision timescales between the grains for different sources of relative velocity. So we've got Brownian motion and turbulence, and we find that they're incredibly large. So it's very significantly inhibiting collisions. And you can see, by comparison, the uncharged dust collision timescales in the dashed lines there. So we've got self-consistent chemistry, ionization chemistry for the inner disk, and with self-consistent dust grain charging, and we lump it all into a full disk model called QDisk, which has been developed in-house with all these interesting processes and further prescriptions for MRI activity in the inner disk. And we're looking at things like the viscous instability and the potential for planet formation. So if you have any questions about any of the modeling or any of our early outcomes, please talk to me.
So, hello everyone. I'm Luigi Zaglio, second year PhD student under the supervision of Giovanni Rosotti. And right now I'm at ISO, working on my, working with Anna Miotel and Miguel Vioque, doing my one-year studentship there. So, one of the main goals of my PhD is to develop and benchmark a new technique to extract protoplanetary gas disk properties using barely resolved observations. So, the perfect test bed for this is the data coming from the ALMA decollage program, which has a moderate angular resolution, and we have a lot of disks, so 18 total, over 4 different star-forming regions. So there you see a continuum, the collection of the continuum images. So if you jump on the other image, that is 12CO emission, so I'm focusing on gas observations. And on the first row, you see the image data. On the second row, the image model that I'm fitting to the data, and the residuals that do not show any 3 sigma contours, so this is a good fit. So basically, in order to extract these informations, I'm using visibility fitting. And if you want to chat more about that, I'm very keen on it. I'm very looking forward for that. I'm using a model that I developed that allows to retrieve this geometry, stellar mass, vertical heights, temperature, and also a collection for the optical dots. The main questions that I'm interested in with this work is to answer at what typical radii lies the material that is being used to build planets, then can we put empirical constraints on disk evolutionary scenarios, and also how does the disk vertical structure evolve with time. So if you want to talk about visibility fitting or discuss any of these goals, please come talking to me. Thank you.
Hi, my name is Brianna Zawadzki, and I'm a postdoc at Wesleyan University. I'm going to be sharing some of my work as part of the ARCS collaboration. So ARCS is an ALMA large program. It stands for the ALMA Survey to Resolve Exo-Kuiper Belt Substructures. And so we're observing these debris disks, which are, of course, in the outer disk at least tens of AU from their host stars. But when we observe them at these millimeter wavelengths, we can make connections to the dynamics of the systems as we're probing those millimeter-sized grains. So what I'm aiming to do is pull out as much vertical structure from these disks as possible and see if we can make connections to what the planets or planetesimals stirring the system are like. Thanks.
That's it. Indeed. All right, let's give a round of applause for all our poster presenters. And our excellent guides, our keynote speakers from this morning.